let's look at a new formula. We have a new formula here. It's this one. Once again, it is on your reference sheet. Excuse me. Right there. There it is. You'll notice while you look here on your reference sheet, this formula looks an awful lot like the PERT formula, just with different letters used. And you would absolutely be right. In fact, when we go to label what all these letters mean, you're going to notice a startlingly familiar pattern to the last video. So let's label what the letters mean, because that's your job. You don't have to memorize the formula, but you need to know what they each mean. A of T stands for our final amount. Like I said, very similar to the last video. This A with the tiny little 0 next to it, we call that A naught. A naught is our starting amount. K is my rate of growth. Like I said, very familiar. Now, this is one big difference. K is not just a rate of growth now. It could also be a rate of decay. So K is positive if your amount is growing. K is negative if your amount is decaying or decreasing. And then finally, of course, we have T, which as always is time. So it is the exact same thing as the PERT formula. We're just using new letters for these things. Why we have the same formula with two totally different sets of letters, I don't know. We just do. So once again, it's not your job to memorize it. It's just your job to know what they all mean. So let's try this in example 4. Just like we've done this whole lesson, we're going to read through this, highlight each of the numbers, and label what they mean. So, example 4 says, in order to perform arthrosclerosis research, epithelial cells are harvested from discarded umbilical tissue and grown in the laboratory. A technician observes that a culture of 12,000 cells grows to 5 million cells. So that actually just gave us a lot of information. That 12,000 is how many cells we're starting with. So that's our A naught, 12,000. And it grows to 5 million cells. So that's our A of T. That's how our final amount. And it says it did all of that in 1 week. So that is our T. It says, assuming that the cells grow exponentially. By the way, this word grows exponentially. That's your key word to use this formula. Just like how in the last video you looked for those words compound continuously to know to use the PERT formula, you look for the words grows exponentially, and that tells you to use this formula. Now, what we're doing says find a formula for the number of cells in thousands after T days. So basically, I want to find a final equation where I have A naught and I have K, and I just leave A of T and T, so that in this equation, I can plug in any T and get how many cells are there. So here I know that after 1 week there are 5 million cells. But what if I didn't want 1 week? What if I only wanted 3 days? After 3 days, how many cells are there going to be? So this is the general formula that will tell me that I can plug in any T I want and find out how many cells are there on that day. So to find this general formula, I need to know A naught and I need to know K. Well, I already know A naught is 12,000. I know that one. However, I do not know K. So my first order of business is going to be to solve what K is, so then I can plug that in and I have my general formula that works for any T. So let's use the information we've got here to solve for K. So I know I end with 5 million cells. I start with 12,000 cells. Then I have E. I do not know what K is. That's what I'm trying to find right now, so I can plug it into my formula. And it says T should be in days, so that means 1 week. I'm going to put 7 because I want T to be in days. And now I can take all of this to solve for K. So we're going to divide by 12,000. That gives us 1250 over 3. If we plug that into our calculator and simplify it, e to the 7k. Change the form and flip the input and output. Divide by 7, and that there is my k. That is the rate that this is all growing at. Now, you will notice that very specifically, I am not turning that k into a decimal. The reason I'm not doing that is because that k is not my final answer. Remember, you do not turn anything into a decimal until you know that that something is your final answer. Since k is not my final answer is this general formula that works for any t, I do not want to find a decimal for k. So I am actually just going to copy in this whole thing that I got for k, and I know that my p is 12,000, and there we go. That is a formula for how these cells are growing. So I can plug in any t I want into here, and that will tell me how many cells are on that specific day. Having done one of these, let's try another one. Example 5. This one is about iodine-131. It's a commonly used radioactive isotope that helps detect how well the thyroid is functioning. Iodine-131 decays exponentially. Hey, those are our words that tell us we're going to use this formula. And after approximately 8 days, so there's our time, only 1/2 of the original amount remains. So that is our final amount. That's our A, 1/2. If 5 grams of iodine-131 is present initially, so that's our starting amount, that's P, which also tells us if we're starting with 5 grams, our A is going to be 2.5 grams, 1/2 of the original amount. And then once again it says find a function that gives the amount of iodine in grams T days later. So same thing as last time, this final answer should be a general formula, a general equation that lets me find however much is of this iodine-131 is in the bloodstream at any point T. So at 5 days, at 10 days, at 20 days, I can plug any T in and find out how much of this iodine-131 is left. So same thing as before, I need to know P and I need to know K. I know my P is 5, that's how much I'm starting with. I do not know my K, so this is going to go the same way as last time. We're going to plug in everything else we know to find what K should be. And then I can plug K in to my equation. So once again, I do not, oops, that's the wrong color. I do not know what K is. And my T is 8. So since we've already done an example like this, I would like you to finish solving for K and then plug K into our final equation to get a final function that works for any days that we want. Pause the video and try this one out on your own. Let's see how you did. I solved this for K and I got ln of 1/2 over 8. Notice once again I did not turn that into my decimal because it is not a final answer. So I carry that whole thing over to here and that is my final answer for my general formula that works for any T. Now the nice thing about example 6 is I am actually going to use this formula because example 6 is still about iodine-131 and it still has the same p of 5. So notice all the things that were given are still the same. So I'm going to use the same equation that I just found. With the same k. And let's finish reading the problem. How many days will it take until only 0.0625 grams will remain? So that is an A of t. That is a final amount. So I'm going to erase my A of t and put that in. So it looks like for this problem, I'm solving for t. How much time until this is left? So I want you to walk through how to solve this. Divide by 5, change the form, solve for t. Plug it all into your calculator. I'll tell you right now, the answer looks kind of yucky, but you plug it all into your calculator and get a decimal because the t is our final answer. So now we can get a decimal. Pause the video, try to solve this out on your own, and then come back to check your work. Let's see how you did. So I divided that and I got 1/8. Changed the form and I got ln of 1/8 equals this whole thing t. Now, just so you know, at this point, you have a couple choices. You could divide by this whole thing and then do this. But I personally don't really like fractions in fractions. It gets hard to type into my calculator and I worry I'm doing it wrong. So instead of dividing by this fraction right here, notice that instead I multiplied by the reciprocal. So instead of ln of 1/2 over 8, I times by 8 over ln of 1/2. And then since it's the reciprocal, it also cancels. And then multiplying by the reciprocal over here is a little easier because I can put that over 1 and then just multiply across. So then in my calculator, I can do this, which is a little bit easier to type in. And then if you type that in, you should get an answer of 24 days. So that is all we're going to say about our continuous exponential growth and decay model. In the next video, we're going to move on to some logarithm story problems.